I want to talk today about one of the new radar utilities that we have in 2016. So if you go to raster and go to your radar toolbox, into the utilities, I want to talk about Polarmetric Classification. This is something that comes up frequently with customers. They want to know, do we do Polarmetric Classification? We do. This is the tool for doing it. For 2016, we have several new algorithms in here. The one I'm going to talk about right now is the one we call the Poly basis. This one's fairly popular. A lot of people are interested in it. First thing you have to do, of course, is load your image. I have an image here that is a multipolar radar data set. It's radar sat 2, and you can see we lock in on the product XML to load and view this image. Notice that we have here 8 bands. So since we can only have 4 polarizations, HH, VV, VH, and HV, this has to be a single look complex scene. So we have a magnitude and phase layer for each polarization. So we have 4 polarizations, 2 bands for each polarization. We have 8 bands. So we want to look at that in the viewer. Now, it really is only useful to look at the magnitude layers. The phase layers are not something you can visually interpret, and those are, of course, 1, 3, 5, and 7. So we would make some combination here of the odd bands just because we want to look at the magnitude and not the phase. Oh, sorry, that's oriented to map. As we've talked about before, this orientation to map is done automatically. We take the input image, apply the sensor model to it, reproject it on the fly into the viewer. So we're looking here at San Francisco. We're looking at 3 magnitude layers with different polarizations, and we can see here downtown San Francisco, Golden Gate Bridge here, Oakland Bridge here, Golden Gate Park is here, that sort of thing. Airport is down here. In order to use this particular algorithm, we have to give the band assignments because, of course, I don't know a priori what the band assignments will be. Different satellite vendors sometimes use different combinations. You may only have 4 bands instead of 8. So I can't know this in advance. How are we going to know? We have the tool here. We can go to multispectral, take the drop-down list, and it tells us what we have. So we see that HH is band 1, which it already is. VV is 3, so we'll have to change that. VV is 3. HV is 5, so HV is 5, and of course this one then has to be 7. So input here, the same scene, and we'll give it some sort of an output name like Poly image. And then, of course, we would push OK to do the calculation. But we have several options here. You can see in this case I've elected to despeckle the image a little bit. All radar image has speckles, so it doesn't hurt to suppress it a little bit. I have a 3x3. You can change it if you want, but be cautious. As you make this window bigger, you lose spatial resolution, so you don't want to do that too much. And then we also have the option here, we can post filter it. And again, we can change the size there. Post filtering I would probably apply if I was, for example, trying to classify a vegetated area where we have large fields or forests or whatever, fairly large areas. A city, I kind of want to keep my high spatial resolution, so I'm not going to post filter this particular image. And when I'm ready to calculate, I would just hit OK and the calculation would continue. I have, of course, already done this, so we don't have to waste a lot of time sitting watching the progress meter go. So here's my Poly image. Again, I would orient it to map. I always do that. We'll fit the frame here, clear the display. Okay. Now this then is the same image, but we've done a classification based on basically what we call the bounce mechanism. How did that wavelength interact with the target as far as it bounced off this, it bounced off that? That's kind of the phenomenology we're utilizing to interpret this stuff. We can zoom in a little bit here. So we're looking at downtown San Francisco, Golden Gate Bridge here. And in fact, you can see the bridge, and we have a double reflection here where we have a bounce off the bridge, but also we have a return where it bounces off the water and then off the bridge. So we're getting echoes there from different bounces off different surfaces that are separated in space. This is a time delay there. Notice, for example, though, that we have our residential area. We see a lot of red in these. That's because we have a double bounce in these areas with buildings. So we're bouncing off the road and off the side of the building or things like that. In the city, you have a lot of double bounce. But notice this residential area here, we're not getting that strong double bounce return. And it's because, if you'll notice, everything is oriented differently. The look direction is basically from this side here, so we're looking in this direction. So here we have the beam coming in pretty much perpendicular to the architecture, and so we're getting a nice clean double bounce. Here, where it's interacting with the city, the beam is coming in and hitting at an angle. It's probably bouncing, hitting and bouncing away. So we're not getting a strong double bounce return. Those are the sort of things that make these polarization classifications hard to interpret. Yes, we understand if we have a double bounce, we can map that. So we're not getting a double bounce here, for example, or a double bounce here. But whether or not we get a double bounce also depends on the orientation of the target to the beam. So we're not getting a strong double bounce here, even though this is a residential area, probably very similar to this one, oriented differently. So this polarization stuff is hard to interpret. That's why classification hasn't become real popular or user-friendly. We can come down here. Here's the airport. Airport has, of course, flat runways here. So the beam comes down, hits the runway, and skips off. So on these flat surfaces, we tend to get a dark return. Same thing out here in the water. Water's a little bit rougher, but it's still pretty flat. But you can see here in the terminals, we're getting a very strong return here, right? The beam's coming in, hitting this infrastructure, and bouncing off. So we can interpret these scenes, but you kind of have to know what you're doing. Which is true of radar in general. It's not an easy thing to work with. But here we definitely see residential infrastructure, that kind of stuff, metal, right angles. We're getting this strong double bounce return. So we can see a bridge coming across here. You can see obviously, communities or human infrastructure built along these roads. We get this strong radar return. So that's in general how you'd interpret a polarization image when you try to classify it. You have to know what you're doing, but if you do, the tools are there to let you do that sort of stuff. So that is how you would do a polarimetric classification in 2016. So thank you very much and good luck.